In this paper, we work on the setting of image captioning with multiple sources of input image encodings, or views here. For example, an input image can be encoded by a sequence of detected objects, image grid features, text descriptions, and so on. Given these multiple views, in this paper, we tackle the research problem of how to efficiently and effectively leverage these views. For efficiency, we propose to regard each view as an augmentation of the input image and encode each view with a shared encoder independently. We also add a contrastive loss across views for representation learning. Overall, our formulation improves computation, parameter, and label efficiency. For effectiveness, we propose a hierarchical decoder layer to first model the effectiveness of each view and then adaptively aggregate each view according to their effectiveness. In this paper, we focus on the vision and language task of image captioning, where given an input image, the model has to generate a sentence describing the input image. Traditionally, researchers propose to encode the input image into a sequence of objects by a pre-trained fast CNN, or they use a ResNet pre-trained on ImageNet to encode the input image into image grid features. More recently, in our previous work, we proposed to use clip multimodal retrieval to effectively encode the input image into text descriptions and achieve substantial performance improvement. Now we have encoded the input image into multiple input image encodings, or we call it views afterward. And in the future, more and more views could be incorporated when the stronger pre-trained models are available. Therefore, the research problem here is how do we better leverage these views to do better in the image caption task? For an encoder-decoder transformer model, one research problem is how to efficiently encode these views. A common approach is to concatenate all the views into a long sequence, which is computationally inefficient. Another common approach is to train a separate encoder for each view, which is parameter inefficient. Furthermore, the transformer model is intrinsically data hungry. Therefore, we also need to take care of label efficiency. Given multiple input views, another research problem is how to effectively decode these views. Since different views have different noise levels, the model should adaptively weigh each view according to their effectiveness. Take the figure on the left as an example. When predicting the next word of sofa, let's say if the object detector fails to detect sofa, then the model should downweigh the view of detected objects and leverage other views with the sofa information to better predict the next word of sofa. In order to encode the input views efficiently, we propose to regard each view as an augmentation of the input image. Just like what we do with data augmentations, we encode each view independently and reduce the computational complexity from quadratic to linear, which is computationally more efficient. For the same reason, we encode each view with a shared encoder and reduce parameter complexity from linear to constant, which has better parameter efficiency. Since now we regard each view as an augmentation of the input image, we add a contrastive loss across views to help representation learning. This allows the model to achieve better label efficiency. Furthermore, the contrastive loss does not require ground truth image caption pairs. This allows us to train the model in a novel semi-supervised fashion. In order to decode the views effectively, we propose a hierarchical decoder layer to adaptively aggregate the views according to their effectiveness. The Level 1 cross-attention module first aggregates within each view at a token level individually to model the effectiveness of each view. And then, the Level 2 cross-attention module aggregates across views at the view level jointly to adaptively aggregate each view according to their effectiveness. We first evaluate our method HAAV, which is a trained-from-scratch small model on the MS-COCO dataset. Compared with other large-scale pre-trained larger models, our method achieves comparable and usually better performance despite using only a trained-from-scratch small model. We also train and evaluate our method on the Flickr 30K dataset to demonstrate the label efficiency of our method. Since our method incorporates contrastive laws across views to improve representation learning without relying on labeled captions, we therefore train our model in a novel semi-supervised way by incorporating unlabeled images from MS-COCO dataset. In the supervised training setting, our method achieves substantial performance improvement compared with other train-from-scratch smaller models. By incorporating additional unlabeled images and train our model in a novel semi-supervised way, our model is able to achieve additional performance improvement on top of the already strong supervised results. We further conduct a series of analyses to show that our method indeed has better computation, parameter, and label efficiency. As we can see from the table below, our method only has linear computational complexity and constant parameter complexity. And on the right figure, we can see that our method only requires about 50% of the label data to achieve comparable performance as other common formulations. Despite being more efficient, our method achieves the best performance compared to other common formulations. That means we do not sacrifice performance in pursuit of efficiency. We also conduct analysis to show that our method is capable of adaptively weighing each view according to their effectiveness. In the first control study, we add random noise to a view and measure the attention weights at each caption generation step. As shown in the figure below, the attention weights toward the noise view drops consistently across all caption generation steps. In the second control study, we mask out dog in one of the input views and measure the attention weight at the step of generating the word dog. As we can see from the figure below, the attention weight toward the masked view indeed drops consistently across different attention heads. Overall, our hierarchical decoder layer learns to adaptively weigh each view according to their effectiveness. Thanks for listening. More details of our method can be found in the following link, and we also release our code and the augmented views in the following link. If you're interested in our work, please come to our poster presentation session on Wednesday morning. Thank you.